I'm Martin Molan, participant of Summer of HPC 2019, and today I'll be talking about exploring the faults of HPC systems. So, I've been doing my project here in the supercomputing site in Bologna, and the data work comes from two HPC systems, namely Galileo and Marconi. And of course, different systems and different sections of the systems have different architectures, which infers the data I can collect. But roughly speaking, I have two kinds of data. Physical data, which is data collected about CPU frequencies, temperatures, and stuff like that, and high-level fault reporting, which actually reports the state of the HPC system from the user perspective, meaning what sort of faults prevent users from actually using that HPC systems. And in my project, I will mostly focus on the second partition of the data. So, when thinking about what sort of models we can do based on the data we have collected, of course, the first thing that comes to mind is anomaly detection. We want to create a model that learns what is the baseline operation and then detects anything that deviates from the baseline. The problem with this is, the limitation of anomaly detection is that, of course, we can only detect whether or not something is a fault. We need a separate or other model to actually detect what kind of fault do we have. Working further on that idea, we also want to create a fault prediction model. For instance, we want to understand how the different anomalies refer to actual usability of the system. We want to understand what sort of we want to be able to understand and to predict what sort of faults the supercomputer will have. Working on that, we will be able to we could be able to construct, for instance, a predictive maintenance model. And the third one is that we actually want to understand the nature of different faults of the supercomputer. We want to understand which sort of faults raise errors, but do not actually prevent the supercomputers from functioning, do not warrant the shutdown of the systems, and which faults are serious enough to actually cause the downtime of the system. So, first two models would fall under the umbrella of black box models, where we only want a prediction, and the third one would fall under the category of white box model, where we also want, of course, the prediction, but more importantly, we want to understand the problem. We want to understand the reason behind the predictions. So, now for the technical stuff, and to explain what I managed to do in the summer school and what will be done on top of the work I did here. So the raw data set is of course the whole data set is extremely big, and it's in appropriate file format, which means that we cannot process it all in RAM, which means that we have to do batch processing. And the raw data set is in that sort of shape. For each timestamp, for each attribute, for each node, we have its own line. This state is, of course, unusable for machine learning, which means that we have to write a pipeline which will transform this data set in batches, in parallel, into a shape appropriate for machine learning. A shape appropriate for machine learning would be this. For each node, for each timestamp, we have a single line where we have the values for all the attributes that we're interested in. So, as explained earlier, the big part of my project was to write a high-performance parallel pipeline that does this transformation efficiently. This data set can then be the basis for all the possible models I described earlier. So, but now going to the node state. We have two different information gathered from the high-level monitoring system. First one is about node state. Zero state means that the node is functioning perfectly, and 1 means that there is a sort of warning, and 2 means that there is a fault. But of course, not all faults warrant the downtime of the system. And of course, our goal would be to understand which faults are serious enough to cause downtime. For instance, this node here has some sort of warning, some sort of fault, which was then corrected by systematic statements. Speaking of, here we explore faults. This is each line is a single node, and these are different timestamps. So, for instance, we want to understand all the nodes that are colored red for classes 1 to 6 warrant the downtime of the system. And we would like to understand what is the correlations between the warnings, between the faults, and the faults that cause the downtime of the system. So this was roughly the overview of my work here. And of course, this is just the beginning of the larger, hopefully, work that will further explore the faults of HPC system. So thank you for listening, and that was it for my part.
Should I press the red button?
Yeah.